the scratch on the screen there. So behind this, inside here, there's a light bulb. It's unpolarized light. All these lights are unpolarized. So it coming up this way, and they just project it on it. Okay, let me turn off the light. See better.
Definitely yesterday.
Light. Oh. Okay.
Was it on my laptop? No, right?
Okay, so we have here polarizer, which you probably have seen before. These polarizers, right?
Is your sound off?
Just like your sunglasses.
Is your sound off?
Your sunglasses is a polarizer.
You just turned it on.
It actually does your polarizer. So when you you can go home and do this experiment again. If you have a sunglass and it's going to block the light, horizontal light, because when you are driving, you don't want to see the light bouncing off the road onto your eyes. Right? So it blocks out the horizontal light, and then that the vertical one, it blocks out half. Okay, so here is a polarizer. So if I, that's the light intensity. That's I naught. Okay, that's I naught. Now that light passes through a polarizer, right? So you see darker and the brighter. So this is I naught right here. That's the intensity I naught. And passing through a polarizer, this is half I naught.
Is it separate?
It's darker, right? But it's darker, half I naught. Now, if I have another Polaroid, which is the second polarizer there, it's called the analyzer, right? The reason it's an analyzer is that I can rotate this one and then see what kind of light passes through it. Okay, so if I lay this perpendicular, what do you see? It's completely dark where the two overlap. Okay. It turns out that the polarization of these polarizers is along the long direction. Okay, so this is the long direction. So if I have these two polarizers this way, we say that the two polarizers are crossed. Because they are 90 degrees from each other. The two
This like sunset lamp?
axes are 90 degrees from each other. That means that there's no light that can pass through.
For the pickle part?
Agreed?
Okay.
Because the first one comes out polarized along the vertical direction, and the second one that's laid on top of it only passes horizontal component. Therefore, it completely blocks. Okay, now I can rotate this. That's why it's an analyzer. Okay, I can rotate this, and then I'll go through 180 degrees, and then see how many maxima and minima you see. So we start with the two dark, right? Dark.
Focus on it.
This way, dark. And then I rotate 45 degrees, right? It got darker, a little bit brighter. And then now is the maximum, right? Maximum amount of light. And then 45 degrees. Rotate this way. And now we get a minimum again. And then bright, super bright, brightest. And then the intermediate intensity, and then dark. Okay? So how many, through 360 degrees, how many minima do we see? Two. How many maxima? Two. Okay. All right.
That's actually okay.
Let me put another polarizer. Okay, I have these two cross, right?
How does it go?
Now, if I let's say have a now there's no light coming through, right? The darkest area where they cross, the two cross. Now I put an intermediate one, another one, in between. Okay, in between. So where the three overlaps, do you see intensity? without it, you don't see, right? This is the area you want to focus, where the two overlaps. Okay, only that area. Only when the polarizers overlap. It's the dark, no light, no light passing through. I put a one in between at 45 degrees. And then we have this way, which is dark, and this way, which is, alright? So I rotate the middle one, you see that the intensity of the transmitted light varies. Right, varies. And if you don't have the intermediate one, they are dark.
It's a puppy.
So you need to analyze this in a
Doesn't it
stepwise
look like a
fashion.
pig?
What's wrong with a pig?
Let's say the
Is it
first
inside
one
of it
here, and then the
You
second
don't like
one,
pigs?
you'll have this one here, right? If it's blocked by the second one, what happens if I put this on top of the other two? Nothing gonna happen, right? Because there's no light coming through that dark area. Right? This area you wanna focus on. This dark area,
Messages, yeah.
right? Because there's no light.
Why
It
we
doesn't
want-
matter what you do with this top one. It's always dark, right? Because there's no light coming through.
How is
to
there
the
so
third
many?
polarization.
Is there another Chrome tab open?
Okay, now if I rotate this one here, say 45 degrees,
Oh.
there's some light,
It's because of this.
and then you can do this one here, there's some light coming through,
Does it even have
and then you can
thing?
completely annihilate it to dark. And you just have to do this one polarizer at a time. So you start out with this, half the light is cut out, and then if they are crossed, zero light. If they're 45 degrees partially, if they are aligned, maximum intensity. If you have this way, and then you can, if you have this polarizer already at 45 degrees, like this,
You said
after
that
the
to me.
second one, the electric field
Just
is
let me see.
oscillating
Can you?
along the second direction, the direction of second polarizer. Always, always. Okay, the polarization is always defined by the
Let me
last
send this to me, thank
polarizer
you.
that it goes through. Because that's the only intensity that can pass through electric field. So it's along this 45 degrees. So now you have a direction 45 degrees. And then that can then, well, the third one, if you lay it 45 degrees, basically all the light goes through. And then it'll extinguish all the light if it is perpendicular to this direction. Okay, so if it's perpendicular, like this direction, you see that they are completely dark.
Why are you harassing everybody?
Got it?
Who's this?
Okay?
Oh,
So
this is like
these
Israeli
polarizer
Yeah.
questions, you do one at a time.
Another Oh, okay. Who's this?
Ooh.
This.
Okay, so
I see it.
you need to
Oh, yeah, I
understand
remember.
how to analyze this. Current carrying
That's like on Discord.
loop or wire, loop in this case, in a magnetic field. Whenever you have a current carrying wire in a magnetic field, there's going to be a force, right?
Oh, oh.
Oh,
What was it?
this cable.
Oh, that was really scary. That was so loud.
That's not part of the demonstration.
Oh, you recorded it?
Although it's very exciting.
But like, how would you
Okay.
so that 80% has an I don't think you can.
All right. So if you have a current carrying wire, right, have the I, and then in the magnetic field, then you have I cross B, and then this length of the wire, and then that will be equal to the force, right? So any current carrying wire in the magnetic field, these can be steady, no changes, and you have a force. Okay, the current in magnetic field can also change in time. It's still given by this formula. Okay, as long as there's a current, right, and as long as there's a magnetic field, and these current magnetic field can be either steady or changing in time. There's always a force given by this formula. Okay. All right, so what we have here then, a solenoid, right? These windings and these bars in the inside just to make it stronger magnetic field. Right? If you have just like a dielectric, right? Dielectric material between two plates, right? You can increase the capacitance. You can store more charge, right? So here we have the same thing. You have winding wire here, but you have to wind many, right, to get some kind of magnetic field. Or you can wind certain amount of turns, and you put these iron rods in here. And these iron, just like the dielectric, in the magnetic field case, you put magnetic material, like iron, which is magnetic. And that increases the magnetic field that can be created. Okay, so in this case, we have a ring. This is wire is broken. Oh. I'll show you this one here. This wire is broken. Okay, this one here, if I have if this wire is not broken, then if I change the magnetic field, it's going to induce a current, and this light bulbs we're going to light up. Just show that there's a current. Okay, but this, unfortunately, the wire is broken, and I don't have a tool to fix it. Okay. Okay, now go to the next experiment. So we have a ring of copper. Okay, and ring of copper, we're going to put it in here. So it's in the magnetic field.
It's gonna flow.
Okay, so when I turn on, okay, when I turn on the pass the current through this coil solenoid, it's going to have a changing flux, or it's going to have a magnetic field, and it's going to have a changing flux through this loop. And a changing flux then will create a current in this loop, copper ring, which is loop current, the metal ring here. And that current in a magnetic field is going to have a force on this ring. Okay. So let's see. So this is a transformer, which when you plug it in, you can vary the voltage that comes out. Anywhere from 0 to 140, but 120 is the maximum you can get.
Like, Art doesn't know a lot of
Okay,
information. Art doesn't know a lot of information. Not like the
Oh,
see that?
yeah.
Okay. So that's the force. That's the force. Push that button, it sends a current through this. Right, sends a current. And because it starts from zero current, zero magnetic field, current through this, and then creates a magnetic field because it's solenoid. So that magnetic field starts from zero and then increases to some amount, right, in a very short time. So that means that the flux is changing through this loop because the magnetic field is changing in time from zero to something, right? So it's changing in time. So there's a induced current in this. Okay. And then there's an induced current, and then if you have B field, which is actually in the direction this way, and there's a current, and then it'll create a magnetic field pointing up.
It's okay. And then what?
Do that again.
Like, even, it's gonna be dropped anyway.
Okay,
It's
watch
not
now.
gonna be created anyways.
Yeah. Jumps. So the force is which direction? Up. Okay. Now, this is aluminum. Aluminum. So the force you see here, the force is proportional to the current. Okay, so Faraday's law says that there's a voltage generated, and the current is equal to the voltage, which in this case we have this formula here, and then the resistance. Okay, so the resistance of copper versus aluminum, which one has lower resistance, or which one has lower resistance? Copper or aluminum? Copper. Okay, because that's why all the household wires are made of copper, because it has lower resistance than aluminum. Aluminum also tend to oxidize. Yeah.
Fun.
Okay, so this one here has higher resistance, aluminum. So the higher resistance means that the induced current is going to be smaller. Induced current is smaller, what that means that this thing will jump higher or lower than
Lower?
this? Lower. Okay, let's see. Let's assume that you remember how high the copper jumps. So life is all relative. All right. One.
Oh, that was higher.
Higher. This is higher.
Yeah.
So what does that tell you? What does that tell you? The resistance is lower,
That's what I said.
but the resistivity
Oh.
is
Oh.
higher. Then you have to go
Resistance
to
is
the
lower,
geometry.
resistivity is higher.
Okay, geometry. See, this is the thin one. This is a thick one. Right?
Oh, that's why. Okay.
So the resistance, remember the resistance, right? See, that's why the exam is cumulative. R is equal to rho L over A.
Oh.
So it depends on the geometry.
So the A.
So the diameter is
What's
the
up?
same, so the length is about the same,
Length.
but the thickness is, the
Length of-
cross-sectional area
Oh, okay.
is larger, right? So the A is bigger,
So the resistance.
but A is in the denominator, so the resistance goes down.
Mm.
The resistance goes down, given the same magnetic field flux change, the current induced could be higher in the aluminum because it has a lower resistance. Therefore, it jumps up higher. Make sense? Physics always makes sense. This is the aluminum, but with a cut in between. It's cut. Right? So how high is it going to jump?
Because the length is decreased.
We do the experiment.
Okay. Oh, okay.
Nothing, because there's no current. It's cut, right? Which is same thing. It's a coil which generates which is solenoid, and it's going to have magnetic field up, pointing up, pointing sideways. It's going to be there's a magnetic field when I have current in here. Okay. And then this is a familiar object to you, Coke can, right? So I'm going to put the Coke can inside here, and then we see what happens when I pass a current through this. Okay, so now
It's a
I have
sinusoidal,
to figure out.
like wire. I don't know. Huh?
I go.
That's just where like the other stuff is. Like the stuff you see right there. It's like the same thing on the other piece.
Okay.
It's a bomb.
Okay, I put this. Make sure it's plugged in.
Okay.
Make sure it's
My brother like coded
turned
it.
Yeah.
on. And this one that I tripped.
I can do that.
Why?
I can
do
do
it,
it. If you pay for my membership,
Sure,
I can do
it's
it.
just fine.
Okay, no, I don't know
I
what
think
that is.
it's free. It's free.
Okay, but it's probably not the same.
Why?
Okay, it's not tripped. Okay, now I switch on. I put the Coke can in first. It's a perfectly round cylinder. You see, huh? Round.
I would believe him.
I put it in here. And I turn this on. So that means that it's,
The
what it
entire
does
time
is when I
it's been
turn
going
on, it charges up this capacitor. This is what a capacitor looks like. It's a big one, so it can store a lot of charge.
Okay.
And then when I, when you see, maybe I switch this toggle down, okay? It's supposed to be charging.
I think it's a biological reaction to be scared of like that noise, right? Oh! Did you see the flash?
Verify the switch is toggled down.
I don't think it's gonna work anymore.
Toggle.
Like you saw the flash, right?
Yeah,
I think it.
Okay. I put
Oh, so
this
we can't
in
do
and I
we can't do
charge
pickleball.
it on board.
Let's just do henna. Let's not do pickleball. Let's just do henna.
2 minutes. I have to wait 2 minutes. Being the capacity, I have to do a lot of charge. Right? Charge. When I toggle this switch down, it'll discharge the capacity. So because there's lots of charge, when I toggle down, there'll be a big current that's going to flow in the circuit through this.
Can we have the sign-in sheet?
Huh?
The sign-in
Oh yeah,
sheet?
sign up sheet.
Thank you.
Yeah. Oh, wow. Okay. So that's why you forget these things when you are.
Should we start at the front so you don't have to walk?
Yeah.
Thank you. Okay.
Okay. Yeah, sign fast. And then if you don't find it, then sign it on your way out. Okay, 120 times
Yeah.
2 minutes, 120, 150. Okay. Okay, so I'm going to switch the toggle down. And we'll put your discharge the capacitor. That's the discharge. That's how much charge is in there.
Oh my gosh.
And then I take a look
That scared me.
at this can.
Should I
So, what happens is that there's a force. There's a force this way and also this way, right? But it's constrained in there. So the force is all radial. And that's why it goes down. So what happens is that the you have current, right? That's flowing in here. And then there's a magnetic field, which is pointing actually sideways. Yeah. Sorry. So up. Yeah. In this case, it's up, and so the force is going in. So I have a diagram that I'll show you next time. how that-
Yeah.
That is
Take your laptop.
caused by the induced
your
current in this
Mm-hmm.
can,
Show me your laptop.
going this way.
Okay.
Induced can, and then it's going this way, right? Circling this way, and then the force, the magnetic field, if you say up, right, and then the force will be in. Okay, current going this way, magnetic field up, then the force is in, radial. Okay, so that's the force that's created by the changing current, the induced current in a magnetic field.
Should I pause it? Should I stop it?